Well, hello everyone, and sorry that I was unable to attend our regularly scheduled class. So today what we're going to do is take a look at how we can do numerical differentiation. I expect that all of you have actually done that before, but maybe you just have not necessarily known that a particular proc or in SAS or function R was actually essentially doing it for you. Today's lecture is to give you some basic background on how numerical differentiation is done, so you have a better understanding what procs and functions do. But also, I would anticipate that in your own research, you may have a need to do numerical differentiation. So this lecture will hopefully help you. So let me get over here to the notes on page 1. So in your very first in your calculus class, your first calculus class, you learn the basics of what a simple derivative is. And let me get a red pen out here. Oops. Okay. And so basically it's just you take the limit as h goes to 0 of your function evaluated x plus h minus your function evaluated x divided by h. And so essentially what you're doing here is you're looking at, well, what's the change in the y direction, if you think of it in terms of being plotted, over the change in the x direction. And we're trying to make this change in this x direction get very, very, very small, and this gives us our derivative, or essentially a slope that we're looking for. Now, the numerical derivative is essentially the same, but we do not do the limit part. And so we pick a particular small value of h that's greater than 0, and then evaluate this expression here. And on page 2, we have a nice little diagram that shows what's going on when you're doing that. So in this diagram here, we would like to be able to estimate the derivative of the red line when it's evaluated at the point x. And so what that basically means is that you are trying to find the slope of this tangent line when it intersects the red line there at x. Now, when we do this in a numerical manner, we are actually finding a secant line where we evaluate f of x at x and also x plus h. Again, h is going to be a positive number, a little bit greater than 0. And so what we end up with is 2 points where this line intersects our ultimate goal, this red line. And we're actually computing then the slope of the secant line there. Now, as you can see through this diagram here, you can see that it's kind of about the same as what the tangent line is, but it's definitely not perfect. And so, whenever we take a numerical derivative, we have to be concerned about, well, how accurate this numerical derivative is. So because of that, too, there are other ways that one could find a numerical derivative that perhaps might be better. One would be, instead of looking at f of x plus h, look at f of x minus h instead. But to be honest, this has very similar possible inaccuracies as the first way that we were calculating a numerical derivative. What's actually more accurate is to use what's called a central difference formula, where now we look at f of f evaluated x plus h, and we subtract off f evaluated x minus h, and we divide by 2h. Notice how we're looking at h units to the right of x, h units to the left of x, and so now instead of that change in x being h, it's actually 2 times h. And so for some small number greater than 0, for h, we simply evaluate this expression, and that's a very common way that numerical derivatives are actually done in practice. But just how accurate is this? So what we can do is evaluate accuracy, and this is done throughout statistics, by looking at Taylor series expansions. And so just to review what a Taylor series expansion is, since, I don't know, maybe for some of you it's been a little bit. Let's say I'm interested in f of x, evaluated at some point x sub 0. And so, what you learn in your first calculus class then You evaluate then f at f of x0, and then you take the first derivative of f. The way I'm going to denote derivatives here is by using a little dot on top of the function. Take the first derivative evaluated at x0, take x minus x0 and divide by 1 factorial. Then we continue looking at the second derivative evaluated at x0, take x minus x0 squared divided by 2 factorial, and you can keep on going. And so oftentimes in statistics what we do with a Taylor series expansion is that we try to approximate f of x by maybe cutting off the expansion after maybe these terms, or maybe also adding these terms. In fact, a lot of asymptotic statistics is just simply based upon that. Okay, so that's the basics of a Taylor series expansion. And what I would like to do is go back to here, do a Taylor series expansion of this term, and also this term right here, and see, after that subtraction there, what is left over. Okay, so first of all, f of x0 plus h, here's my entire Taylor series expansion for it. I'll let you verify the details on your own. Now I'm going to subtract off f of x0 minus h. Here's that Taylor series expansion for that. Now what you're going to notice is that we have some simplifications that occur. So for example, these terms cancel out, as do the terms involving the second derivatives too. And this is what we're left with then. So this would be then again the Taylor series expansion of what's in the numerator of the central difference formula. Now also in that central difference formula we divide by 2h. So let's go ahead and divide this term, or this expression, by 2h. And notice how we have a 2h here, so that ends up canceling out. A 2 here ends up canceling out and leaves behind an h. And so then our central difference formula simplifies down to this expression. Now the really cool thing here then is, look what's left. That first derivative of f evaluated at x0. And that's what exactly this is trying to estimate with the central difference formula, is the actual derivative evaluated at x0. But we have some other stuff here. And so we note that this formula is not going to be, or this central difference formula is not going to give you the exact first derivative evaluated at x0 unless the third derivative or higher for this f function is equal to 0. But still, so in fact what this is often referred to as then is a remainder term. But still, we can see that this remainder term is often going to be quite small because we're dealing now with third derivatives there. And remember that this h here, this h, remember, is some small number that's greater than 0. Okay, so let's talk about then, just how good the central difference formula is in an actual example. So the corresponding code here is in derivatives_examples.r. And we're just simply going to take a look at a very simple function. F of x is equal to x3 minus 5. And we're going to be interested in this function from x equal 1 to 4.5. So we want to actually approximate the derivative within that range. Well, since this is such a simple function, we can, of course, calculate this first derivative. It's 3x squared. And let's look at a graph of the function and the derivative itself. So I create a function in R called fx, for the lack of a better name, that's going to allow me to evaluate this function at x3 minus 5. I use the curve function to plot the function, and this is what we get. Okay, so again, it's a very simple function, and what we want to do is be able to approximate the derivative from 1 to 4.5. Well, of course, I can find the actual derivative. So I'm going to create a function called fx dot dot. And that needs to be 3 times x squared. I'm going to create values of x0, sequence of numbers from 1 to 4.5 by 0.5. And then let's start off with a small h value of 0.0001. Now in this next data frame here, what I do is I find the actual true derivative by evaluating my fx dot function at x0. But then also I look at the first way that we looked at calculating a numerical derivative. And then also I look at then the central difference formula to calculate the numerical derivative. Okay, so the goal is to have everything equal to that true.dir column. And we can see with the first way of calculating a numerical derivative, we get quite close, but it's not exactly the same as the true derivative. With the central difference formula, we actually get a lot closer, at least with respect to 2 digits of accuracy, we get it right on. We get the true derivative completely correct. One could even go ahead and show, what will be then the approximate error by just taking a look at that first term and that remainder, and you can see that this first term is actually quite small, and that's why you see, at least to 2 digits, that the derivative from the central difference formula is exactly the same as the true derivative. So you might be thinking, okay, well, this h has to be a number that's small, close to 0. How about we just make it smaller and make it maybe as small as we can, and by doing that, your numerical derivative is going to be more accurate. Well, you could do that, make an h extremely small, but the problem is actually the accuracy does not, even though mathematically we see that the accuracy should get better in terms of smaller. In terms of the difference between the true derivative and the numerically calculated derivative, that measure of accuracy that should get closer and closer and closer to 0, at least mathematically we see that. Unfortunately, though, due to the numerical precision limits of a computer, that's not necessarily the case. So let's look at h equal to 10 to the negative 7th power. Before we did 10 to the negative 4th power. And we can see that even the first derivative case here, or first numerical derivative case there, gets the true derivative correct to 2 decimal places, where before it did not. So that's good. How about we let h be 10 to the negative 14th power? Now notice that both ways to calculate the derivative are now showing some inaccuracies. So they're not exactly equal to that true derivative. And what happens then when we get to h raised to the 10 to the negative 16th power? Big errors. It's saying that all these derivatives are equal to 0. And the reason being is because a computer only has so much accuracy, and basically it's going to, when it takes this difference here, f of x evaluated at x0 plus h minus f of x evaluated at x0, when it takes that difference there, since h is just so small, it sees this difference as essentially equal to 0. And so you got to be careful about, yes, you want to choose a small h, but you can't choose an h too small, because then you can have very big accuracy errors. Okay, so let's take a look at a way that we can do these numerical derivatives in a little bit more automated manner. And we're going to focus on the pracma package to do that, where the prac comes from the word practical, and the ma comes from math for practical numerical math functions. So it's a nice little package in R that will do these numerical derivatives for us. We're going to focus first on the f-deriv function that will calculate these numerical derivatives up to the 8th order using the central difference formula. Okay, so we can go back to the same example that we were looking at before. We'll shortly get to a statistical example. And so if I say f-deriv, I put in my function that I want to take a derivative of as my first argument, f. Then what I want to evaluate then this derivative at, that's the argument x, we're going to put our x0 there. Remember, x0 is a sequence of numbers from 1 to 4.5. I want the first derivative, so that's what the n corresponds to. I'm going to set my h to be 0.0001, and the method that I want to use to do these numerical derivatives is the central difference formula. Let's also do exactly the same thing and put into save 2 where we use a smaller h. And then lastly, in save 3, we're going to use the f deriv again, but now we're not going to specify what h is or what method is. The default method is central difference, and the default way to find h is actually it finds it on its own. So let's see what happens here. Excuse me. Unfortunately, I didn't actually include the true derivative, but I will tell you that, or what we've seen before when we took h equal to 0.0001, of course we did get our numerical derivative was the same as the true derivative, and so we can use this as a guideline there. So when we take 10 to the negative 14th power, we get what we were seeing the same errors as what we were seeing before. And if we let f deriv find an h on its own, notice it gets everything right. What about higher order derivatives? Well, again, our function is f of x is equal to x cubed minus 5. So the first derivative is 3x squared. The second derivative is 6x. The third derivative is 6. A fourth derivative is 0. So by just changing the values of n, I'm able to find my derivatives. And you can see that for the second derivative, indeed, for all my values of x, I get it right. For the third derivative, I get it just about right. And the fourth derivative as well, I get it just about right too, because all these numbers are quite close to 0. Now this package actually contains other ways to do some of these numerical derivatives. You can take a look at it on your own if you are interested. Okay, next let's take a look at a statistical example where we can use numerical derivatives. And we're just going to do a very simple one involving the Bernoulli distribution and finding the maximum likelihood estimate for the probability of success parameter. The reason why I chose this is because we know what the correct answer should be. Simply the observed number of successes, you could say, divided by the number of trials. And so, oftentimes whenever I do something for the first time, such as in research, I try to always pick a simple example to verify that, let's say, my code gets what I know is correct if I were to analytically derive something. Okay, so, excuse me. So, back in your Stat 883 days, you've learned what the likelihood function is for let's say, n different Bernoulli random variables. You've learned the log likelihood function. You've probably derived then the maximum likelihood estimate. So let's say that the number of observed successes is 4. We're going to call that W. And the number of trials is 10. We'll call that N. Then in a very general way, the log likelihood function, where pi is our probability of success parameter, we're going to denote that by a script L there. That's equal to w times the log of pi plus n minus w times the log of 1 minus pi. And if we were to try to find the maximum likelihood estimate, then the first thing that we would do is find the derivative of the log likelihood function. And that's simply w divided by pi divided by, w divided by pi minus n minus w divided by 1 minus pi. Next, we would set this equal to 0, solve for pi. And if you do that, you find the maximum likelihood estimate is w divided by n. In other words, the proportion of successes. So let's take a look at some R code that helps show this, and then we'll start looking at the derivatives in a numerical manner. So I'm going to set w to be 4, and rather using n, I'm going to use n1. The reason being is because n is used in the f deriv function, so I need to use something else. So we'll call n1 is the number of trials. That's going to be 10. Then I simply program in my log likelihood function. This is one way to do that. There are other actually more efficient ways to do it, but I think this is good enough for now. Then what I'm going to do is plot the log likelihood function as well. And this is what we get on page 11. And you can see on the x-axis where we have pi, y-axis log of the likelihood function, we can see that the maximum of this log likelihood function occurs when pi is equal to 0.4. Again, 4 divided by 10 is 0.4, so that's why that occurs. Then we can find the derivative of the log likelihood function. We can actually program it in. We've already found the derivative, so this is how I program it in, and then I use the curve function to plot it, and in red is what we get. So again, pi on the x-axis, the derivative of the log likelihood function with respect to pi is on the y-axis, and we can see that at pi equal 0.4 that the function itself is equal to 0, and so that's why the maximum likelihood estimate was 0.4. Let's look at how we can do some of this stuff using numerical derivatives. So I'm going to create a function called partial.log L2, pass in values of pi, w, and n1. Fderiv is going to allow me to find the derivative of log L that we had already created before. I'm going to take the derivative with respect to pi. I'm going to find a first derivative, and using the ... component of fderiv, I'm going to pass in the data. So if I find the derivative with respect to pi and evaluate it at 0.4, the maximum likelihood estimate, notice what I get here? Well, just about 0, which of course is what we would want to get. I can also look at multiple values I can also evaluate the function at multiple values at the same time, so 0.4 and 0.5, so we get about 0 again, and then we get -4 when we are no longer at the maximum likelihood estimate. How about we actually then plot the numerical derivative of the log likelihood function, and that's what I did here using blue. I plotted from 0.05 to 0.95 on the x-axis, and we can see how that numerical derivative is essentially exactly the same for all values of pi in that range as what we know what the actual first derivative is. And so that helps confirm that indeed we are doing everything right. Now there's another little function I want to tell you about that's not necessarily dealing with derivatives here, but it's a very useful one. We'll actually come back to it in the optimization section that we will do after this, and that is the uniroot function. This helps you find a root of an equation when you only have, let's say, one root that you need to find. Excuse me. So, to find a maximum likelihood estimate, of course, you set your estimating equation, which is the first derivative of the log likelihood function, set it equal to 0. So what we're doing is essentially finding a root of that equation. That's our MLE. And so if I once again use my function that finds the numerical derivative of the log likelihood function and specify an interval to find my root in, let's say 0.01 to 0.99, I pass in also my data with a ... argument. Then what uniroot does is tries to find the root of the equation. And guess what? It gets the 0.4, our maximum likelihood estimate that we've gotten before. So it can be a very useful function in simple optimization problems. Okay. Let's take a look at a little bit more complex example where a closed form expression for the maximum likelihood estimate does not exist. And also let's say that there are actually, in this case, there are two maximum likelihood estimates that one need to find for the two parameters. So we're going to look at the gamma distribution now. And so using a Castello-Berger parameterization, we can write out our likelihood function. It's a function of two parameters, alpha and beta. Our data is going to be in y. I guess here, since I have a y sub I there, I should probably maybe make this a vector of y's there. And one can simplify the expression for the log likelihood function is this. Sometimes, though, in actual programming instances, as you will see shortly, it's not really worthwhile to actually simplify. So instead, what one could do is just leave the likelihood function as essentially this. Okay, we'll come back to that shortly. Now, for the log likelihood function, then, what we can do, apply simple properties of logarithms, and again, this is what we get. Alternatively, one could write then the log likelihood function as then the sum from I equal 1 to n of log of f of y. Okay, we will be actually using that very shortly. Obviously, that's not a simplified version of it, but in a computational code setting, often it's easier to use this version and actually more accurate. Okay, so let's get some data from a gamma distribution so that we can use that to find some derivatives and also eventually maximal likelihood estimates. So I'm going to set a seed number here, and I'm going to simulate some data from a gamma distribution. A sample size of 30. My alpha parameter is going to be 7 divided by 2, and my beta parameter is 2, and those two things together give me a chi-square 7. So to simulate from a gamma distribution, I simply use the R gamma function. Again, sample size of 30, shape parameter alpha, scale parameter beta. This is what my simulated data looks like. Again, 30 observations, and you can see that it's going to be likely a kind of right skewed. So let's talk about how to write out the log likelihood function. There are a number of ways that you can write it out. This is the most efficient way that I'm going to show you. Even though you might be tempted to write it out in terms of, let's say, some simplified expressions, based upon what you would do by hand, that is actually not necessarily the most computationally efficient way to write a R function. Also, you could be leaving yourself open for numerical errors as well by writing it out that way. So this is the most efficient way. So log L is going to be my function name. I'm going to have an argument called theta for my function. Theta is going to have two components where the first one's going to be alpha, the second one's going to be beta. I just simply put them together in a vector. The reason why I do that will be more clear in the optimization section. Next, I give what my data will be. So inside the function, I find n, simply as the length of y, specify alpha and beta, and here's the important part right here. This is the log likelihood function. So this is log L. And again, the way I'm doing this then is taking the sum I equal 1 to n of log of f of y given alpha beta, rather than using some kind of simplified version of the log likelihood function. So let's take a look inside the sum part here. So d gamma stands for density gamma. Here's my data. Remember, this is going to have 30 elements in it, so I'm going to evaluate my density function 30 separate times, and I'm going to get a vector back in return. I specify a particular value of alpha, a particular value of beta, and this is one of the most important parts here. With pretty much all like d gamma, d binom, d whatever distribution function you're using, there's typically always an optional argument called log. The reason being is because very often you're using a log likelihood function, and to help speed up the process and to be more accurate, R almost always provides a log argument where you say true. So what this is going to give me then, and I'll highlight this for emphasis, the stuff that's highlighted in blue in terms of the code gives me my log of f of y. Now notice the sum part here. Well, this d gamma, again, is going to give me a vector of 30 elements because I'm passing in 30 elements in there for y. And what I need to do is sum all those log f of y values. So I just simply sum. And there's my log likelihood function. I didn't have to worry about using any kind of maybe factorial. I didn't have to worry about using the actual mathematical gamma function at all, or log gamma function at all. I just simply use d gamma itself. Okay. So I'm going to again use stuff in the pracma package. I'm going to use a new function called grade, I should say, because this is going to find the gradient in terms of it's going to take the derivative with respect to alpha, and it's also going to find a separate derivative with respect to beta, and then evaluate everything then at the corresponding data values. So I specify log L. I'm going to say do the derivative with respect to alpha and beta, and then evaluate it at y. And so that I get the following here. So the first derivative with respect to alpha is 1.16. The first derivative with respect to beta is 4.87. I should also point out, in case this wasn't clear, this alpha and beta here are actually what we're evaluating these derivatives at. 7 divided by 2 and 2, what we had set on before. Also, if I were to use the grade function once again, but I could also evaluate at the maximum likelihood estimates. We will find these in the optimization section. We can see that the numerical derivatives, when they're evaluated, are approximately 0 for both, which again makes sense for these maximum likelihood estimates. I should also point out that the grade function there uses central differences. Now, one thing that we often are interested in is to find an estimated covariance matrix for our maximum likelihood estimators. And the simplest way that you can do that when you're doing maximum likelihood estimation is to find the Hessian matrix, find the negative of that. That's the observed Fisher information. And let me start over again. Find the Hessian matrix, find the negative of it, and then evaluate the negative of that Hessian matrix at the corresponding maximum likelihood estimates, and then you get the observed Fisher information matrix. If you invert that matrix, then you get the estimated covariance matrix using the basics of maximum likelihood estimation stuff. And so note the small little changes there in blue. And so I can use the Hessian function here to find my a matrix of second derivatives. And notice how I'm evaluating them at the MLEs. And then using the solve function in R, that allows me to find then the estimated covariance matrix then. So for example, this 0.594, that is the estimated asymptotic variance of beta hat. Here's the estimated asymptotic variance of alpha hat. And here is the estimated asymptotic covariance of alpha hat and beta hat. And note that we didn't, in the end, we didn't have to derive anything. All this stuff is automatically done for us by using the corresponding numerical derivative functions. So that can be very helpful when you are, let's say, programming in your own maybe statistical method that you've developed. Instead of maybe working with some very long equations, one can get this stuff almost automatically through using these kinds of techniques. Well, what about symbolic differentiation? Well, there are some functions that kind of help you do that. The d function in the deriv function in R, that's in the main R there. You don't have to download any package for that. And these functions know about some mathematical functions, as you can see here, but not necessarily all possible mathematical functions when it actually takes derivatives. So here's just a very simple example using my f of x is equal to x cubed minus 5 example once again. Let's come on down here. So here's my f of x equation. F of x function that we've seen before. And if I use the capital D function with it, notice how I have to say for the first argument expr, and then I actually have to say, okay, R, this is an actual expression. Don't do any math with it. X cubed minus 5. Take the derivative with respect to x, and we get the symbolic derivative returned to us. The deriv function works somewhat similarly, but it actually provides you a function that you can use then whenever you want to actually evaluate that first derivative at a particular value of x. So for example, if I say deriv expr equal tilde, here's my actual function I'm interested in, and I want to evaluate at potential values of x and do the derivative with respect to x. What we end up getting then, if I just look at eval save 1, notice how I've already set some particular values of x, we see the actual f of x, and then we see f dot of x as shown there. You do a similar thing with the Hessian matrix as well. I'll let you take a look at that on your own. Notice the particular argument there, Hessian equal true. Now, in terms of doing symbolic differentiation, my tool of choice is always to use some kind of mathematical software such as Maple. And so just kind of for emphasis of that, I show you some Maple code there that shows how to do it. I really wish I would have known the existence of these kinds of mathematical software packages when I was a student taking like a course like STAT 882, 883, because I would have basically used that to do a lot of my homework assignments. So lastly, some final notes on numerical differentiation. The diff function does not find any kind of derivative. It actually finds lag differences. In particular, for those of you who are familiar with time series analysis, you know that x evaluated at time t and x at time t minus 1 is a lag 1 difference. And that's what the diff function does. The num deriv package contains a lot of functions similar to the ones that we found with pracma, and those can be useful as well. Okay, so that concludes this little lecture on doing numerical derivatives.